गुड मॉर्निंग, गुड इवनिंग, गुड आफ्टरनून, जिथे जो टाइम है ग्रीटिंग एक्सेप्ट कर रहे हो. पेज नंबर 270. Topic is photon spin. Let us consider the spin of a photon and its relation to the Riemann sphere. Photons do possess a spin, but because they travel at light speed, one cannot consider the spin as being about a fixed point. Instead, the spin axis is always the direction of motion. Photon spin is called polarization, which is the phenomenon on which the behavior of polarized sunglasses depends. Take two pieces of polarized, put one against the other and look through them. You will see that generally a certain amount of light comes through. Now rotate one of the pieces, holding the other fixed. The amount coming through will vary in one orientation where the transmitted light is at maximum. The second polarized subtracts virtually nothing from the amount coming through, while for an orientation chosen at right angles to that, the second polarized cuts down the light virtually to zero. What is happening is most easily understood in terms of wave picture of the light. Here we need Maxwell's description in terms of oscillating electric and magnetic fields. They have a picture over there in 6.26. A plane polarized light is illustrated. The electric field oscillates backwards and forwards in one plane called the plane of polarization, and the magnetic field oscillates in sympathy, but in a plane at right angles to that of electric field. Each piece of polarized lets through light whose polarization plane is aligned with the structure of the polarized. When the second polarized has a structure pointing in the same way as that of the first, that all the light getting through the first polarized also gets through the second. But when the two polarized have their structure at right angles, the second polarized shuts off all the light getting through the first one. If the two polarized are oriented at an angle to each other, then a fraction cosquare of that angle is allowed through the second polarized. In the particle picture, we must think of each individual photon as possessing polarization. The first polarized acts as a polarization measure, giving the answer yes if the photon is indeed polarized in the appropriate direction, and the photon is then allowed through. If the photon is polarized in the orthogonal direction, then the answer is no, and the photon is absorbed. Here, orthogonal in the Hilbert space sense does correspond to at right angles in ordinary space. Assuming that the photon gets through the first polarized, then the second polarized asks the corresponding question of it, but for some other direction. The angle between these two directions being some angle variable as above, we have a cosquare of the same variable now as the probability that the photon makes it through the second polarized, given that it has passed through the first one. Where does the Riemann sphere comes in? To get the full complex number array of polarization states, we must consider circular and elliptical polarization. For a classical wave, they are illustrated in image 6.7. With circular polarization, the electric field rotates rather than oscillates, and the magnetic field, still at the right angles to the electric field, rotates in sympathy. For elliptical polarization, there is a combination of rotational and oscillatory motion, and the vector describing the electric field traces out an ellipse in space. In the quantum description, each individual photon is allowed these alternative different ways of being polarized, the states of photon spin. To see how the array of possibilities is again the Riemann sphere, imagine the photon to be traveling vertically upwards. The north pole now represents the state of R in a square bracket that angle bracket of right-handed spin, which means the electric vector rotates in an anti-clockwise sense about the vertical as the photon passes away by the south pole, represent the state L in the angle bracket of left-handed spin. We may think of photons as spinning like rifle bullets, either right-handed or left-handed. The general spin state R in angle bracket plus Q of L bracket is a complex linear combination of two and corresponds to a point labeled Q on the Riemann sphere. To find the connection between Q and ellipse of polarization, we first take the square root of Q to get another complex number P. P is equal to square root of Q. Then we mark P instead of Q on the Riemann sphere and consider the plane through the center of the sphere, which is perpendicular to the line joining the center to the point marked P. This plane intersects the sphere in a circle, and we project this circle vertically downwards to get the ellipse of polarization. The Riemann sphere of Q still describes the totality of photon polarization states, but the square root of P of Q provides its spatial realization. To calculate probabilities, we can use the same formula half 1 plus cos theta that we used for electron. So long as we apply this to Q and not P, consider plane polarization. We measure the photon's polarization first in one direction and then in another at angle to it. These two directions corresponding to values of P on the equator of the sphere subtending angle at the center, because the P's are the square roots of the Q's and the angle theta subtended at the center. The Q point is twice the rising from the P point theta is equal to of the same variable angle. The probability of yes for the second measurement, given that it was yes for the first, that is, the photon gets through the second polarity given that it got through the first one, is half 1 plus cos 2 of that angle variable, which by simple trigonometry is the same as cos square of same variable asserted above. I get the Riemann sphere, but I have to read the polarization thing again. It does make sense and it doesn't. Okay, objects with large spin. For a quantum system where the number of basis states is greater than 2, the space of physically distinguishable states is more complicated than this Riemann sphere. However, in the case of spin, the Riemann sphere itself always has a direct geometric role to play. Consider a massive particle or atom of spin n by h Planck over 2 taken at rest. The spin then defines an n plus n state quantum system. For a massless spinning particle, that is one of travels which at the speed of light, such as photon, the spin is always a two-state system as described above. For a massive one, the number of states goes up with the spin. If we choose to measure the spin in some direction, then we find that there are n plus 1 different possible outcomes depending upon how much of the spin turns out to be oriented along that direction. In terms of the fundamental unit Planck h bar h by 2, the possible outcomes for the spin value in that direction are n, n minus 2, n minus 4, 2, 2 minus n or negative n. Thus for n is equal to 2, the values are 2, 0 or n minus 2. For n is equal to 3, the values are 3, 1, minus 1 or minus 3, etc. The negative value corresponds to the spin pointing mainly in the opposite direction to that being measured. The case of spin 1/2, that is n is equal to 1, the value 1 corresponds to yes and the value minus 1 corresponds to no in the descriptions given above. Now it turns out though I shall not attempt to explain the reasons that average spin state up to proportionality for a spin n by 2 is uniquely characterized by an set of endpoints on the Riemann sphere, that is by n directions outwards from the center. These directions are characterized by measurements that one might perform on the system. If we measure the spin in one of them, then the result is certain not to be entirely in the opposite direction, that is, given one of the values n, n-2, n-4, 2n, but not negative n. In the particular case n is equal to 1, like the electron above, we have one point on the Riemann sphere, and this is simply the point labeled q in the above descriptions. But for larger values of spin, the picture is more elaborate, and as I have described, although for some reason it is not very familiar to physicists. Riemann sphere, I've seen it in the modern day IBM quantum programming languages. It's interesting, but still it gets on top of my head. There is something rather remarkable and puzzling about this description. One is frequently led to believe that, in some appropriate limiting sense, the quantum description of atoms or elementary particles or molecules will necessarily go over to classical Newtonian ones when the system gets large and complicated. However, just as it stands, this is simply not true, for as we have seen, the spin states of an object of a large angular momentum will correspond to a large number of points peppered all over the Riemann sphere. More correctly, the angular momentum is described by a complex linear combination of such arrangements with different number of points, since there are many different total spin values superposed. In the case of a complicated system, this only makes the total picture even less like that of a classical angular momentum. We may think of the spin of the object as being composed of a whole lot of spin 1/2s pointing in all the different directions, and these points determine only a very few of these combined states, namely where most of the points are concentrated together in one small region of the sphere. That is, where most of the spin 1/2s point in roughly the same direction will correspond to the actual states of angular momentum that one normally encounters with classical objects such as cricket balls. We might have expected that if we choose a spin state for which the total made of spin is some very large in terms of Planck h by 2, but otherwise at random, then something like a classical spin would begin to emerge. But that is not how things work at all. In general, quantum spin states of a large total spin are nothing whatever like classical ones. How is it then that correspondence with the angular momentum of classical physics is to be made, whereas most large spin quantum states actually do not resemble classical ones? They are linear combinations of or orthogonal states of each of which does resemble a classical one. Somehow a measurement gets itself performed on the system, and the state jumps with some probability to one or the another of these classical like states. The situation is similar with any other classically measurable property of a system, not just angular momentum. It is this aspect of the quantum mechanics which must come into play when our system reaches the classical level. I shall have more to say about this later, but before we can discuss such large or complicated quantum systems, we shall have to have some feeling for the odd way that quantum mechanics actually deals with systems involving more than one particle. Many particle systems. Quantum mechanical descriptions of many particle states are unfortunately rather complicated. In fact, they can get extremely complicated. One must think in terms of superpositions of all the different possible locations of all the particles separately. This gives a vast space of possible states, much more than or for a field in classical theory, We have seen that even the quantum state for a single particle, namely a wave function, has the sort of complication that an entire classical field has. This picture, requiring an infinite number of parameters to specify it, is already a good deal more complicated than the classical picture of a particle, which just needs a few numbers to specify its state. Actually 6 if it has no internal degrees of freedom, such as spin. This may seem bad enough, and one might think that to describe a quantum state for two particles, two fields would be needed, each describing the state of one of the particles. Note a bit of it. With two or more particles, the description of the state is far more elaborate than this. As we shall see, the quantum state of a single particle is defined by a complex number for each possible position that the particle might occupy. The particle has an amplitude to be at point A, and an amplitude to be at point B, and an amplitude to be at point C, etc. Now think of two particles. The first particle might be at A and the second particle at B. Say there would have been an amplitude for that possibility. Alternatively, the first particle might be at B and the second at A, and that also would need an amplitude. Or the first might be at B and the second at C, or perhaps both particles might be at A. Every one of these alternatives would need an amplitude. Thus, the wave function is not just a couple of functions of positions, it is one function of two positions. To get some idea of how much more complicated it is to specify a function of two positions than function of position, let us imagine a situation in which there is only a finite set of possible positions available. Suppose there are just 10 allowed positions given by orthonormal states 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 in angle brackets. The state psi of a single particle would be some combination psi is equal to z0 of 1, z1 of 1 plus z2 plus of 2 plus z3 of 3 up to z9 of 9 in angle bracket, where the various components z0, z1, z2, z3, z9 provide the respective amplitudes for the particle to be at each point in turn. 10 complex numbers specify the state of the particle. For a two-particle state, we need an amplitude for each pair of positions. There are 10 raised to power 2 is equal to 100 different pair of positions. We need 100 complex numbers. If we merely had two one-particle states, that is two functions of position, rather than above one function of two positions, we should have needed only 20 complex numbers. We can label these 100 numbers as z00, z01, z02 up to z99, and corresponding orthogonal basis vectors as 0, 0, 01 in angle bracket, 02 in angle bracket up to 9 by 9 into the same ket and bra vector. Then the general two-particle state psi would have the form of psi in angle bracket is equal to z00 of 0 and 0 angle bracket plus 0 z01 of 0 and 1 plus up to z99 of 9 9 in angle bracket. This product notation for the states of the following has the following meaning. If alpha in angle bracket is a possible state for the first particle, not necessarily a position state, and if beta in angle bracket is a possible state of the second particle, then the state which asserts that first particle's state is alpha and the second one is beta would be written as alpha into beta in angle bracket. If the products can also be taken between any other pair of quantum states, not necessarily single particle states. Thus, we always interpret the product state alpha into beta as describing the conjunction. The first system has a state of alpha in angle bracket and the second system has state of beta in angle bracket. A similar interpretation would hold for alpha in angle bracket, beta in angle bracket, gamma in angle bracket, etc. However, the general two-particle state actually does not have this product form, For example, it could be alpha beta plus p into sigma, where p in angle bracket is another possible state for the first system and another possible state for the second. This state is linear superposition, namely the first conjunction plus the second conjunction, and it cannot be re-expressed as a simple product. That is the conjunction of two states. The state alpha beta minus IP, the same symbol as another example, would describe a different state, such linear superposition. Now, the quantum mechanics require a clear distinction to be maintained between the meanings of the word and plus. This is very unfortunate tendency in modern parlance, such as in insurance brochures, to misuse plus in the sense of and. Here we must be a good deal more careful. The situation with three particles is very similar. To specify a general three-particle state in the above case where only 10 alternative positions are available, we now need 1000 complex numbers. The complete basis for three-particle states would be they just keep adding the product to it, 000 up to 9999. Particular three-particle state have been in a form of alpha, beta and gamma, where alpha, beta and gamma need no to be in position states, but for the general three-particle state one would have to superpose many states of this simple product kind. The corresponding pattern for more or more particles should be clear. The discussion so far has been for the case of distinguishable particles, where we take the first particle, the second particle and the third particle, etc. to be all of different kinds. It is a striking feature of quantum mechanics. However, for an identical particle the rules are different. In fact, the rules are such that in a clear sense, particles of a specific type have to be precisely identical, not just say extremely closely identical. This applies to all electrons and it applies to all photons, but as it turns out, all electrons are identical with one another in a different way from the way in which all photons are identical. The difference lies in the fact that electrons are fermions, whereas photons are bosons. These two general kinds of particles have to be treated rather differently from one another. Before I confuse the reader completely with such verbal inadequacies, let me explain how fermion and boson states are actually to be characterized. The rule is as follows: if the psi is a state involving some number of fermions of a particular kind, then if any two of the fermions are interchanged, the psi must undergo into a negative of psi. If psi involves the number of bosons of a particular kind, then if any two of the bosons are interchanged, the psi must undergo psi remains psi. One implication of this is that no two fermions can be in the same state. For it, they were interchanging them would not affect the total state at all. So if we would have to have negative of psi is equal to psi, that is psi is equal to 0, which is not allowed for a quantum state. Okay, fermions cannot be in a same state. That's interesting. Which is not allowed for the quantum state, because that becomes a 0 if it becomes a negative psi. This property is known as Pauli's exclusion principle, and its implication for the structure of matter are fundamental. All the principal constituents of matter are indeed fermions, electrons, protons and neutrons. Without the exclusion principle, the matter would collapse in on itself. Let us examine our 10 positions again, and suppose that now we have a state consisting of two identical fermions. The state of 0 in angle bracket is excluded by the Pauli's principle. It goes to itself rather than to its negative under interchange of the first factor with the second. Moreover, 0 and 1 angle bracket will not do as it stands, since it does not go its negative under the interchange, but this is easily remedied by replacing it 0 1 minus 1 0. This is similar to the what we were discussing in the first chapter. This is very similar, where we were discussing Turing machines, a halting problem, and Pauli's exclusion principle is similar to that, very similar in a quantum mechanics. I don't know if those are anyhow. An overall factor 1 by square root, they're not same, 1 by square root of 2 could be included if desired for normalization purposes. This state correctly similar but not similar. The state code correctly changes sign under interchange of the first particle for the second, but now we do not have 0 1 in angle bracket and 1 0 as independent states. In place of those two states, we are now allowed only one state in all. There are half 10 into 9 is equal to 45 states of this kind, one for each unordered pair of distinct states from 0 and 1 and 9 in angle bracket. Thus 45 complex numbers are needed to specify a fermion, 2 fermion state in our system. For 3 fermions we need 3 distinct positions, and the basic states looks like 0 1 2 plus 1 2 0 plus 2 0 1 minus 0 2 1 minus 2 1 0 minus 1 0 2. All numerics in angle bracket are being 10 into 9 into 8 by 6 is equal to 120 such states in all. So 120 complex numbers are needed to specify a 3 fermion state. The situation is similar for a higher number of fermions and 2 bosons, and for a pair of identical bosons and independent basis states are of 2 kinds, namely states like 0 1 plus 1 0 and states like 0 0, which are now allowed in bosons, which was not allowed in fermions, giving 10 into 11 by 2 is equal to 55 in all. Thus 55 complex numbers are needed for 2 boson states. For 3 boson states we need a similar kind of calculation, and it is actually 220 complex numbers, and so on. Of course, I have been considering a simplified situation here in order to convey the main ideas. A more realistic description would require an entire continuum of position states, but the essential ideas are the same. Another slight complication in this is the presence of spin. For a spin 1/2 particle necessary a fermion, there would be 2 possible states for each position. Let us label these by up spin up and down spin down. Then for a single particle we have, in our simplified situation, 20 basic states rather than 10. But apart from that, the discussion proceeds just as before. So for 2 such fermions we need 20 into 19 by 2 is equal to 190 numbers. For 3 we need 20 into 19 into 18 by 6 is equal to 1140, etc. In chapter 1 I referred to the fact that according to modern theory, if a particle of a person's body were exchanged with a similar particle in one of the bricks of his house, then nothing would have happened at all. If that particle were a boson, then as we have seen, the state psi would indeed be totally unaffected. If the particle were a fermion, then the state psi would be replaced by negative psi, which is physically identical with psi. We can remedy the sign change if we feel the need by simply taking a precaution of rotating one of the 2 particles completely through 360 degrees when the interchange is made. Recall that fermions change sign under such a rotation, whereas boson states are unaffected. Modern theory as of around 1926 does indeed tell us something profound about the question of individual identity of bits of physical material. One cannot refer strictly correctly to this particular electron or that individual photon person. To assert that the first electron is here and the second electron is over there is to assert that this state has the form of 0 1 in angle bracket, which we have seen is not allowed for a fermion state. We can, however, allowably assert there is a pair of electrons, one here and one over there. It is legitimate to refer to the conglomerate of all electrons or of all protons or for all photons. Individual electrons provide an approximation to this total picture, as do individual protons or individual photons. For most purposes, this approximation works well, but there are various circumstances for which it does not. Superconductivity, superfluidity, and the behavior of a laser being noteworthy counterexamples. The picture of the physical world that quantum mechanics has presented us with is not at all that we had got used to from classical physics, but hold on to your hat, there is more strangeness yet in the quantum world. The paradox of Einstein, Podolsky, and Rosen. That's our next topic. This is going to be an interesting topic. Actually, I have read a paper about it, Bridge. I'm going to continue on this paradox of this Einstein, Podolsky, and Rosen in the next video. Thank you very much.